Welcome to the 24th lecture of the course Turbulence. Okay. So, in the last class we mainly talked about the velocity profile and the friction laws for turbulent channel flow. As we have mentioned that these two aspects of turbulent channel flow are very important, and we already derived the velocity profile as well as the friction law, okay, based on our various arguments. So, today mainly we are going to talk about the turbulent statistics, okay, in turbulent channel flow, okay, and budget of the kinetic energy equation. Okay. So, these are the main thing we are going to talk about today. So, as I have mentioned in the previous class that our main objective for turbulent channel flow to find it out the friction law as well as the mean velocity profile, and we found that the mean velocity profile can be stacked together. For example, very close to the wall we have something called law of the wall, okay, which is found to be, or which is actually universal, because it it is the same form for turbulent pipe flow, turbulent channel flow, turbulent boundary layer flows. So, similarly the log law, and these are sort of universal relations for turbulent pipe flow, turbulent turbulent channel flow, turbulent pipe flow, and turbulent boundary layer flows. Whereas, we talked about the defect law, there is no such suggestion here that this particular relation should be universal. Okay. So, with this we would like to start the discussion on turbulent statistics. Okay. So, for turbulent statistics mainly we will consider the tentative variation of Reynolds stresses, okay, and we will mainly follow the turbulent flows by Pope, okay, that particular book. To do that, actually and there is a very important reference in that particular aspect is that turbulent channel flow simulation by Moen and Kim, or Kim et al. Actually Moen, Kim as well as Moser. There are 3 people in this paper, but anyway this particular paper I suggest you all of you to go through, okay, and all along with the wall bounded flows in the book by Pope. Okay. So, anyway, so before we proceed to discuss this turbulent statistics, first we will have 3 different regimes. We will divide the flow area in 3 different regimes. So, there are one is viscous wall region, and we have already talked about this particular region in the last class, which resides y plus less than 50, that is what we talked about. Then our log law region, okay, this is found to be there within 50 delta V y 0.3 delta. Okay. In that region this particular log law is found to be well valid. So, this is another regime, and the last one, let us say it is a core regime, okay, or region. Okay. So, that is for y greater than 0.3 delta. Okay. So, that is what the 3 regime. So, in this 3 regime we will have the variations, I mean how these turbulent statistics are varying, that is what we are going to talk about. Okay. So, let us see the turbulent statistics plot, okay, in turbulent channel flow, and these plots, as I mentioned, that I will draw mainly following the book by Pope, okay, and for details, okay, please go to that book and read, okay, for better understanding as well as for exact value of this, that variation of this, turbulent statistics. So, let us say this is 8 and this scale is, let us say, ui uj bar by u tau square. Okay. So, Reynolds stresses normalized by friction velocity. Okay. So, this is 8, let us say this is your 4 and let us say this is 7, okay, and this is 2, this is 1 and this is let us say 0 and this is what is our minus 1. Okay. So, let us see the variation of various Reynolds stresses. For example, Reynolds normal stress that u, okay, I am drawing very close to the wall only. Okay. So, let us say this is y plus. Okay. So, y plus till 60, it is sort of blown up the near wall area, for example. So, this is let us say 20 and this is 40, okay, 20 and this is this should not be 20, this should be even more blown up because this maxima somewhere close to 12. So, 20 should be somewhere here. Okay. So, 20 should be somewhere here and this should be 40, okay, and later on. Okay. So, it is mainly near the, we are focusing mainly near to the wall here. Okay. How this Reynolds stresses will vary. So, this quantity, so this one, let me use this color. Okay. So, this one u RMS square, okay, that means u square bar. Okay. So, this is what this quantity, and if you see your turbulent kinetic energy, that will also come something similar. Okay. So, this one is essentially K. Okay. K is nothing but your half ui bar. Okay. So, this is turbulent kinetic energy by definition. So, this is what is your K. Then let us show another 3 quantities, which is our this is our W square bar. Okay. Then V. Okay. So, this is V square bar, okay, and Reynolds stress will vary something like this. So, one should be somewhere here. Okay. So, that this is what is your Reynolds stress. So, very near the wall you see how these stresses are varying, when this normalization is done by the u tau square. Okay. So, this is what your URMS square, WRMS square, VRMS square, this is what is Reynolds stress. Okay. This is UV bar. Okay. So, this is negative. So, that means minus UV is positive, keep it in mind. Okay. So, this is what is your variation of these Reynolds stresses very close to the wall. If you see, they will look like that. Okay. Now, let us plot the same thing. Okay. So, why I have blown it up here, that is all because of the fact, you see, close to the wall means in the viscous wall region, the vigorous turbulence activities are there, because your this URMS square is giving a peak here, then similarly WRMS, okay, all the peaks are within this y plus less than 50, means within this viscous wall region. Okay. So, the vigorous turbulent activities are, this plot is saying the vigorous turbulent activities are going on close to the wall. Okay. All right. Now, let us draw another plot normalized by the turbulent kinetic energy itself. So, how it will look? So, let me draw it here. Okay. Similarly, this is y plus in this, and let us say this is 400, y plus 400. Okay. So, that means if this is 100, then this is 200, this is 300. Okay. So, 100, 200 and this is 300, okay, y plus, all right. And this one, let us say it is about 2, okay. And what is this axis? We have normalized this ui uj bar divided by turbulent kinetic energy equation, this, okay, divided by this k, okay. And this is let us say this is 2 and this is 1 and this is 0.5, okay. And let us say this is 1 and this is about 1.5, okay. So, this is 1.5, right. So, if we now plot this, this variation, then it will look like this, okay. So, okay, it will slowly try to come to 0 close to the center line of the channel, okay. So, this is what is your, okay, let me just draw, after that we will draw all this, we will do all other things. So, this is what is our, let us say this is what is our this u square bar, this is what u square bar divided by turbulent kinetic energy, which is sort of constant in the logarithmic regime, okay. Then if we see the other plot, for example, your actually this peak should not, peak should be even closer to the wall, as I said that peak should be very close to the wall, okay. This one should be very close to the wall, and the peak for this, W, let us say it will be something it will go something like this, okay. This is your W square bar, okay, and your V will be something like this, okay. So, this is your, okay, and if you see your this let us say this is minus 0.5, okay, minus 0.5, then this is going to be your, this Reynolds stress quantity is going to be something like this. So, the main point to show this plot is, you see this particular regime which is the log law regime, okay. So, in this log law regime, these quantities, once it is normalized by turbulent kinetic energy equation, they are almost self similar, okay. In this regime they are uniform, okay. So, they are approximately self similar in this particular regime, that is what it actually shows, okay. So, that is what is the point we would like to make it here, okay. The moment you normalize by turbulent kinetic energy equation, whereas in this particular case we see there is a peak value which is happening close to the wall, which is within viscous wall region, okay. So, that is what the point. So, in this, that is the reason that first we have divided in 3 regime, okay. So, viscous wall regime, then log law regime and regime as well as your core regime, okay. So, now if we see the another plot, okay. So, this another one, let me just plot it here. Note that these are just tentative, okay. If you would like to see the exact plot or values in y and x axis, please go to this book by Pope. So, this is let us say this is also 2 and 1, 1.5, 0.5, right. So, this is 1, 1.5, 0.5 and let us say this is what is our production P divided by epsilon. Okay. So, production term essentially we are plotting. If we plot the production term, you see production term close to the wall, once again if you see production term also close to the wall, you will give a peak, after that it will sort of will come something like this. Okay. And similarly, if you plot, so this is essentially your, so this is production by, so this one production by dissipation. Okay. So, and if you plot the shear, okay, so the shear term which is also going to come something similar. Okay. Okay. And for shear the scale is different, keep it in mind. For the shear scale is different. So, this should be 5 and this should be about 20. Okay. So, this should be 10. This is what? This is essentially S k by epsilon. What is S? S is actually S here, S is nothing but du dy for this case. Okay. And k of course is turbulent kinetic energy, epsilon is the dissipation. Okay. So, you see once again very close to the wall, okay, very close to the wall, very close to the wall within your y plus 50, the dissipation, sorry, your production is very high. Later on you see in the logarithmic regime they are sort of constant, and it is kind of, you see 1 means production is equal to dissipation almost, indicating the fact that transport is negligible in this particular area. Anyway, we will know better as we talk about this your turbulent kinetic energy budget. So, from this we see how this Reynolds stress, how these Reynolds stresses vary with respect to y. Okay. So, this is your y plus once again. Okay. So, now from the boundary condition at the wall we can kind of get some idea about this variation with respect to y. Okay. So, using the boundary condition at the wall we can somewhat guess the variation with respect to y. Okay. How we can do that, let us see. Okay. So, that at y is equal to 0 our velocity is 0. Okay. So, this is what is the main boundary condition, and using this let us see how we can get this variation. So, let us consider that fluctuation u. Okay. Let us express this in terms of Taylor series. Okay. So, a1 plus b1 y plus c1 y square, all other higher order terms. Okay. Similarly, we can express our v as a2 plus b2 y plus c2 y square plus higher order terms. Okay. And w a3 plus b3 y plus c3 y square plus higher order term. Okay. So, we can get this variation, or we can very close to the wall, when y is very small means very close to the wall we are talking about. Okay. Then we can express this u v w by this Taylor series. Okay. So, this is sort of Taylor series, and this A1, B1, C1, A2, B2, C2, A3, B3, C3 all are coefficients. So, these coefficients are these coefficients these coefficients are 0, mean, random, variable, okay, variables. So, these coefficients means that A1, B1, C1, A2, B2, C2 and A3, B3, C3 and all other terms are 0 mean random variables, and this expression or this Taylor series has been done at a particular x z location, okay, at a particular x z location and at particular time t we can express this fluctuation using this Taylor series. That is what the point here, right, and these coefficients are 0 mean random variables, right. Now, this coefficients, it is also needs to be mentioned that this coefficients does not vary with x, z and t, okay. So, that is also needs to be mentioned, this coefficient does not vary with x, z and t, okay. So, now we will see one thing, we will apply the boundary condition. If we apply the boundary condition at y is equal to 0, so at y is equal to 0, what is the condition? U is equal to 0, W is equal to 0, okay. Similarly, V is also 0 from no penetration condition, right. So, V is also is equal to 0. If we apply that U is equal to 0, that means what do we get from this? So, let us say this is our equation 1, this is our equation 2 and this is our equation 3, okay. So, at y is equal to 0, U is equal to 0, this implies, okay, this implies that 0 is equal to A1, okay, or A1 is equal to 0. This is because all other y is equal to 0, so U is also 0, so A1 should be 0. So, from equation 1, that is what we get, okay. Similarly, you see similarly A3 is equal to 0, okay, from equation 3, okay. What about the case for V? V is also 0 at y is equal to 0, V is also 0 from the no penetration condition. So, then A2 is also 0, okay. Equation 2, okay. All right. If this is the case, you see now let us apply the or let us consider the fluctuating continuity equation at y is equal to 0 and let us see what we get. Okay. So, del u del x plus del v del y plus del w del z is equal to 0. That is what is our continuity equation general. So, at y is equal to 0, so that at y is equal to 0, then this should be at y is equal to 0, this should be considered at y is equal to 0, this also should be at y is equal to 0. Okay. That is what we should consider then. Now, the flow, the flow we are considering, it is a channel flow, and we are considering fully developed channel flow. Fully developed channel flow is homogeneous in x as well as in z. That means this del u del y at y is equal to 0 is basically 0, because there is no variation of any statistics for a homogeneous flow, okay, in this panwise direction. So that means from this condition we can say that del u, so this is at y is equal to 0 is equal to 0, this also, this quantity is also at y is equal to 0 is 0. So this says that del v del y at y is equal to 0 is equal to 0, that is what it says, okay. That means if we integrate very close to the wall, then v is very close to the wall looks like to be constant, okay. Very close to the wall v is sort of constant, but the value of that constant at y is equal to 0 is 0, the v is equal to 0, the value of the constant will comes out to be 0 then. That means what it says that very close to the wall the flow is two component flow, okay. So very close to the wall it is a planar flow, because that del v del y is equal to 0, or we can use that equation 2. What is our equation 2? Equation 2 we have considered a2 plus b2y plus c2 y square plus all other term. Now if you consider here del v del y, which is nothing but a2 is already we have got 0, that means b2 plus twice c2 y plus all other terms, okay. At y is equal to 0, this equation, okay, at y is equal to 0, this equation shows this is equal to this b2, okay. So at y is equal to 0, this is b2, which that means this implies b2 is equal to 0 from this condition, right, continuity equation at the wall. So b2 equals to 0, that means very close to the wall our this particular v, then both the terms in this equation, both the terms are going to be absent. So let us see here, that means these three equation at very close to the wall actually can be written as what? U is equal to b1 y plus higher order term, v is equal to your c2 y square plus higher order terms, w equals to your b3 y plus higher order terms, okay. So let us say this is your equation 4, equation 5, equation 6, okay. So very close to the wall, this is what this is the way your actually velocities will vary applying this boundary condition at the wall, okay. Now you see, so b2 is equal to 0 means the way v will show. So what it says that very close to the wall, that means v is 0 at this point, little bit above v is also 0, because the gradient of v with respect to y close to the wall is 0, okay. So that is the reason we are saying very close to the wall. So the point we would like to make, very close to the wall, the flow is a two component flow. We cannot say it actually two dimensional flow, because here u and w is varying in x and z very close to the wall, it is also varying in y. So we cannot say it is basically two dimensional flow, because u w can be function of both x, z and w very close to the wall. So that is the reason we are saying this flow is two components flow, right, very close to the wall. All right, if this is the case, let us see what we get from equation 4, 5, 6, right. So from equation 4 to 6 we can write what? We can write u square bar equals to, so u square bar equals to b 1 square bar y square, okay, plus all other term. Similarly, v square bar can be written as C2 square bar y to the power 4, all other higher order terms. Then w square bar can be written as b3 square sorry, yes, correct, b3 square bar y square plus higher order term, right. And we can also write that uv, okay. So, uv is going to be b1 c2 bar y cube plus higher order term, okay. So, that means the Reynolds stresses very close to the wall will vary as per these equations. So, that means let us say this equation is 4, 5, 6, right. So, let us say this is equation 7, equation 8 and equation 9 and this let us say equation 10, okay. So, these equations, okay, saying that how this Reynolds stresses should vary close to the wall, okay. Now, you see point is that y is very small, it is less than 1. If it is very small, that means the way u RMS square as well as V RMS square and W RMS square are changing, the V RMS square will be even more slower as well as means V RMS square as well as Reynolds stress growth with respect to y or variation that V RMS growth as well as the Reynolds stress growth close to the wall with respect to y will be slower as compared to the growth of u RMS square and W RMS square, okay. For y very small, okay, this is true, this is what these equations showing, okay. So, this and you can see here in this particular case from these equations you see the variation of V RMS square here, okay. So, the way it is varying close to the wall it is much slower as compared to the variation of U RMS square here as compared to the W RMS square close to the wall. So, that means the V RMS that the variation of V RMS as well as your Reynolds stress very close to the wall, it should have been actually like this, okay. I am sorry. So, exact drawing it is available in the book by Pope, okay, Turbulent Flows by Pope. Please note this, okay, the book, okay, by S.B. Pope, okay, and the name of that book is Turbulent Flows, okay. I have already mentioned in the first course handout, okay. So, please read this book and chapter 7 in that book, all these details are available. Not only that, you do all the exercises which are available in this particular book, okay. So, anyway, this variation then, this Reynolds stress variation essentially we can predict from this of Taylor series expansion very close to the wall, okay. And here one thing we need to keep it in mind that value of y here is very small, okay. So, that is what the point here we would like to make, alright. Now, let us consider the turbulent kinetic energy equation, okay. let us consider the turbulent kinetic energy equation for this turbulent channel flow. Okay. Okay. So, let us first consider the turbulent kinetic energy equation which we derived earlier. Okay. So, first we will start with that particular equation, and what was that equation? If we can remember that this is what was our equation. Okay. ui bar del xj equals to del xj. Okay. This was minus p u j bar rho plus twice nu ui small s I j bar minus half ui u j bar. Okay. This is the transport term, right? Pressure transport, viscous transport and your turbulent transport, minus minus this ui uj bar capital S I j minus twice nu small s I j which is what dissipation, right. So, this equation needs to be simplified for the case of turbulent channel flow. If you do that for the turbulent channel flow, so u1 u2, so only one component of velocity. So, if you go ahead with this, see this particular, let me do it. Okay. So, this particular quantity can be called as k, right, that is what we have already mentioned. So, u j del k del xj, okay, equals to, let us consider these two terms separate, del xj. Okay. So, this is what is our p u j bar by rho, this is our pressure transport, okay, plus let us consider the turbulent transport, these two term we will consider separately, then minus this is ui u j bar. Okay. So, this is the transport term, and plus this viscous transport, let us write it separately, twice nu and del xj. Okay. And inside it is going to be ui small s I j bar. Okay. So, this we have kept separately, and this particular quantity and this quantity. Okay. So, this we know as what, production. So, let us call that term to be production plus p, okay, minus this particular term we know as dissipation. Okay. So, this let us call dissipation epsilon. Okay. So, this equation can be put in this fashion. Now, you see here this particular part is going to be 0, right. For turbulent channel flow, the left hand side is 0. If left hand side is 0, that means this equation once again we can write as, before I rub it out, I just wanted to mention one point here. You see, turbulent production is going to be high there where this your shear is also high. Okay. So, that already we have discussed in the case of while we talked about that boundary free shear flows. Okay. So, this is also the case here. So, anyway, or we can write left hand side is equal to 0, then our production, then our dissipation plus let us keep this term twice nu this del xj ui small s I j bar, okay, plus the plus let us write this turbulent transport. Okay. So, that is going to be del xj half ui uj bar, okay, plus pressure transport. Okay. So, P u j bar, okay, by rho should be there, minus should be there. Okay. All right, or P minus epsilon plus, we have to do little bit of algebra. Okay. So, we will keep this term and twice nu, and this term let us do little bit algebra here. Okay. So, this term can be written as, you know, half will come out from small Sij and this 2 will go out, and if we take, then if we multiply this term, then this is going to be, you know, this is going to be ui del xj plus ui plus ui del uj del xi. Okay. This is what little bit algebra with this term, and this particular term you see, this is uj and this is j, right. So, this is, you know, this particular term for the case of turbulent channel flow, that only one gradient with respect to x2 is going to survive, mean with respect to y is going to survive, all other, you know, summation with for j is going to go out. That means, this particular, you know, term we can write as del y, right, minus half ui v, we can write this, because j is equal to 2 only is going to survive. That means, this is what we are going to have at this particular, you know, term. Okay. So, this is what is our turbulent transport term, right. And the last, similarly, the last term you see only, you know, that j term is going to be del x2, statistics of this is only, you know, survive for the case of gradient in the y direction, or j is equal to 2 direction, not for 1 and not for 3. Okay. So, that means, here we are going to get del x2 means y, this minus, you know, p v bar, 1 by rho you can take it out, okay, or you can keep there for the time being. Okay. So, this is the pressure transport, right. This is your turbulent transport, or we can write production minus dissipation plus, you see here, let us see what we can do with this term, okay, del xj, and this can be, this particular term can be written as, you see, del half ui bar and del xj. Okay. And here you see that this particular term can be taken inside, this ui can be taken inside, and, you know, we can write this as, okay. So, let us write it separately, plus nu, the other term which is going to be there, which is you know, nu into, you see, del xj, right. Ui can be taken inside, because then no changes, because from continuity the del ui del xj is 0. Okay. So, that means, you can write the last term as del xj del ui uj bar del xi. Okay. This is what we can do with this term, plus this 2 transport term, which is, you know, so here since it's only function of y, so we can write the total derivative d dy here, and this can be written as half ui bar, sorry, v bar, okay, and the last term we can write as pressure transport d dy, and you know, v bar, okay, 1 by rho we can take it out perhaps. Okay. So, this is what we can write, okay. And for incompressible flow, if rho is constant, we can take rho outside anyway. So, now let us do a little more algebra with this. So, or P minus epsilon plus, you see what is this term? This term is nothing but our k, right, and this variation is only with respect to y. So, this term can be written as d, so d2 k dy2. So, this particular term can be written as this, okay, plus this term which we got here, okay. So, this term is nothing but u, yeah. So, the last term nu into del ui uj bar, sorry, del 2 del x psi del x j, that is what we can write, okay. So, P production minus dissipation plus what is this? This is the viscous diffusion of turbulent kinetic energy. We are writing in such a fashion so that we get this viscous diffusion of the turbulent kinetic energy here, okay. So, diffusion term, viscous diffusion term, this one, plus this term has come extra. We will see what can we do with this term, plus this last two terms are once again is going to be there, okay. So, plus two terms, these two terms d dy minus half ui v bar, okay, and this minus 1 by rho d p v bar dy, okay. Now, see what is little more algebra we need to do with this term, okay. So, little more algebra we will do here. We know that epsilon is equal to twice nu small sij bar, right. So, this we can write as twice nu half del ui del xj plus del uj del xi, you know, once again half del ui del xj del uj del xi, okay. Now, you see this can be written as 1 by 2, 1 by 2, 1 by 4, this 2. So, nu by 2 we get here, and if we do the algebra, then what we get, you see del ui del xj into del ui del xj, okay. We are not writing a square, that is all because of the fact these are repeated indices, okay. So, these are repeated indices, just to note that we are just keeping it separate, plus similarly we get another two term del uj del xi del uj del xi plus plus twice del ui del xj del uj del xi, okay, bar. You see nu by 2, and essentially you see this is a scalar, because both I and j are repeated indices here. So, here this total quantity is a scalar quantity. So, basically essentially this term, when I and j are repeated and this term are exactly same, okay, because I and j both are repeated indices. So, essentially from these two term we can write 2 into del ui del xj del ui del xj, okay, plus 2 into this term, okay, del ui del xj del uj del xi, okay. So, this equals this 2, you see 2 will cancel out, then we are getting that del ui del xj del ui del xj, okay, plus this nu into del ui del xj del uj del xi. Okay. And this particular quantity, by definition, it is known as pseudo dissipation. So, this is known as pseudo dissipation. So, often written epsilon tilde plus this term whatever we are left with del ui del x I sorry j and del uj del xi. Okay. So, epsilon is equal to means this is your dissipation, this is your pseudo dissipation. Okay. So, epsilon tilde equals to pseudo dissipation and epsilon just dissipation. Okay. Please note this. Okay. So, this bar should be there. I have made a mistake here. Okay. That averaging should be present. So, that means this. So, by definition then it does not look good. Let me clean it. Okay. So, by definition that pseudo dissipation is nothing but your del ui del xj del ui del xj bar, or other way del uj del xi del uj del xi bar. Okay. So, this is what is known as that pseudo dissipation, right. So, dissipation is equal to pseudo dissipation plus this term. Let us see what is this term is all about. Okay. So, what we will do, this term we have to do little more algebra. So, let me do it here itself. Okay. Epsilon is equal to what? Epsilon tilde plus, let us write this as del del xj. Okay. And this ui, we can write this ui, okay, del u j del xi. Okay. If we write that, so nu should be there. If you write that, then what you see? We are getting this term plus another term we are going to get. So, that needs to be subtracted minus nu. So, another term what we are going to get, that another term nu ui nu ui del, so another term del 2 uj del 2 uj del 2 uj del x I del xj. Okay. That is what we are getting then, right, and should be bar of course, and let us see what do we get. So, you can take this term inside, right, and this particular term you see how we can write once again, ui is coming out. So, this particular term you see, so then epsilon bar plus this term is nothing but your see this ui can be taken inside. So, this is essentially can be written as del 2 ui uj bar and del xj, right, this term minus you see this you can write as ui, right, del xi, you take it out, then this can be written as del uj del xj, which is 0 from continuity. So, that means this so what it says, epsilon equals to epsilon tilde plus epsilon is equal to epsilon tilde plus this nu del 2 ui uj bar del xi del xj, right. So, let us come back here. Okay. So, that means this epsilon we can replace with this quantity. Okay. Okay. So, this epsilon can be, the dissipation can be replaced. So, in this particular equation this particular term can be replaced with so this particular term can be replaced with minus epsilon tilde minus nu this particular term, which will get cancel out. So, let us do another another line here. So, or if we continue with this equation, we can write production minus epsilon. So, minus epsilon is equal to pseudo dissipation minus nu into del 2 ui uj bar del xi del xj. Okay. What else are there? Plus this term d2 k dy2, okay, plus del 2 ui uj bar del xi del xj, right, plus your d dy turbulent transport minus half ui v, okay, minus 1 by rho d p v bar dy, okay, the pressure transport term. Okay. So, this is what is our equation, and this term and this term gets cancelled. So, finally, what we get? We get 0 equals to production minus that pseudo dissipation, okay, plus nu d2 k dy2, right, plus d dy minus half ui v bar minus 1 by rho d p v bar dy. Okay. So, this is what is our turbulent kinetic energy equation for channel flow. Okay. So, where epsilon tilde is known as pseudo dissipation. Okay. All right. So, now let us see the budget of this particular equation, right. So, and this particular term is known as viscous diffusion, keep it in mind. So, this particular term is propping up from the viscous transport term itself. Okay. So, this term is coming from the viscous transport term. Okay. So, anyway, now if we plot this or budget this for turbulent channel flow, what do we get? Forty, 30, 20, 10. Okay. This is what is our, let us say, y plus. Okay. So, this axis is basically y plus, and this one is our normalized turbulent kinetic energy, let us say. So, this positive part is known as gain and negative part is known as loss. Okay. Gain and loss, and this is 0. Okay. Let us say this is minus 0.2. So, this is about 0.1 minus, this is 0.1 plus, and let us say this is or 0.1, let it stick somewhere here, and this is what is your 0.2 for example. Okay. So, these are some tentative numbers. Okay. These numbers can change little bit. So, the point that how this production term, see production term, what is production term? While drawing we have to also keep our physical argument alive. So, u v du dy, that is what is our production term. u v is going to be 0 at the wall. So, production at the wall is anyway is going to be 0. Okay. So, production is slowly going to increase, okay, and it is going to be maximum where your shear is maximum, that is where tentatively your production is going to be maximum. So, if we draw the production term, so this is your 20, right, this is 10, okay, this is 30, this is 40, okay, this is important to note. So, production term if we draw, so this is going to be this is going to be even steeper. Okay. The peak will be somewhere at y plus 12. Production peak is seen to be there somewhere at y plus near about y plus 12. Okay. So, this is what is our production. Okay. So, production P is going to vary like this. Production P is going to at different y location, production P is going to vary as this curve. Okay. So, now if you see your dissipation, which will show something like this. So, your dissipation term, this is your dissipation D, okay, that whatever dissipation, that pseudo dissipation as per this equation is going to be vary like this. Okay. So, if you see here near this peak production, your production is excess of dissipation, that means the left out turbulent energy is then going to be transported, okay, away from that particular point. Okay. So, that needs to be kept in mind. Wherever production is not going to be dissipation, that particular amount of left out energy is going to be transported away. So, this is what is your production term. Now, if we consider your kind of viscous diffusion term, so that is going to vary. Let me use other color. So, this viscous diffusion term will vary something like this. Okay. This is what the variation of viscous diffusion. Okay. Okay. Viscous diffusion means this particular term nu d2 k dy2. This is the term will vary like this with respect to y. Okay. And if you consider your pressure transport is going to be negligible, which will be something like this. Okay. Pressure transport, this is what is your pressure transport, means your minus d 1 by rho d p v bar dy. Okay. This is what the term, right. So, this is not this d dissipation we have mentioned as let us say this is this, right. We are now left with only one term, that is your turbulent transport. So, turbulent transport, let us use some other color. Turbulent transport is going to be something like this. Okay. For exact variation, please go to this book and figure it out. Okay. So, turbulent transport is going to vary as this. So, this is what is your turbulent transport, that is d dy minus half ui v, this particular quantity. Okay. Right. Yes, this is what is going to vary like this. So, the point here is that the viscous transports this viscous transport is actually maximum at the wall, and at the wall you see your turbulent transport, turbulent production and pressure transport all are going to be 0. That means the dissipation at wall should match. Okay. So, dissipation at the wall. So, if you consider the dissipation, so what was the dissipation? This epsilon plus we got this particular term, right, del 2 ui uj bar del xi del xj, just now we have derived, right. So, at y is equal to 0, this quantity is also 0. So, that means at y is equal to 0, your epsilon equals to epsilon tilde, okay, because this quantity is going to be 0 at the wall. Okay. So, that means the viscous transport, since the viscous transport is going to be balanced with the dissipation at the wall, since all other quantities are going to be 0. And here your pressure transport transports kinetic energy both towards the wall as well as towards the log layer, okay, and pressure transport is very negligible. Okay. Viscous transports energy towards the wall. So, this is what is the turbulent kinetic energy budget for your channel flow. Okay. So, this is needs to be kept in mind. So, this is what I would like to talk about, mainly about this turbulent channel flow. Okay. So, we are not going to extend the discussion much on this in the next class. Okay. We would like to stop here for turbulent channel flow. Only one point before I close, I want to mention that actually the Reynolds number dependency we have not talked about. Whatever we have drawn in the case of Reynolds stresses, variation of Reynolds stresses with respect to y. So, how does it vary for different Reynolds number? It has been observed that those Reynolds stresses are mildly dependent on Reynolds number. Okay. That is what the observations, okay, based on various experiments at various Reynolds number. Okay. So, anyway, I just wanted to mention one thing, you please go through the chapter 7 of the book by Pope. Whatever has been discussed in the last couple of lectures are available in that particular book only, and do all these exercises, okay, to understand better about this flow or about the turbulent channel flow. Anyway, I would like to stop it here. Okay. We will meet again in the next class and we will talk about pipe flow as well as boundary layer flow. Thank you.